So good morning, good afternoon, everyone, in function of your time zone, and welcome to this series of webinar dedicated to bakers and millers. This session today is dedicated to the presentation of raw material selection, how to optimize it. And during this presentation, we will try and share what we believe is a good proposal to make sure that your raw material, your flour in particular, as bakers or millers, are corresponding to the specifications. So during the presentation, if you have any questions, do not hesitate to use the question and answer section to ask any questions, of course, and we will try and answer everything. So let's start. First thing is to wonder what is a good flour. And today a good flour is often seen as a flour that corresponds, that is inside specifications. And then when it comes to specifications, well, this is a target, basically a specification, meaning that this value must be between this and that. We can wonder about specifications as they are designed today. If we ask, so here this is just a simple exercise that we have done using ChatGPT. If we ask artificial intelligence, with basically gathering data from the internet and saying, this is what everyone is doing. If we ask ChatGPT to tell us how do we control bread flour quality, what are specifications for bread flour quality, we will have answers such as protein content. Of course, protein quality is important, but that doesn't mean something. Here again, we speak about protein content. Here there is a mention about the temperature of the flour, so why not, and the granulation. So basically protein and granulation. Question is, do we have the necessary information just by relying on protein quantity and quality and granulometry? And of course, if we ask the question, you can suspect that the answer is no. But this is not just ChatGPT, this is the entire literature that is like that. And this is even what we have learned in school. Here again, this is another example that what we can find in a very serious journal, Baking Business, saying that if you want to make a good sandwich bread, then you need a flour with a protein content between 10 and 11.5%. So this is the theory. And we wanted to make sure that, well, we wanted to know if it was the truth or not. Because if so, it's very simple. We just need a flour with a protein content between 10 and 11.5, and we will always have a good sandwich bread. So we have made the work, and we have analyzed 150 samples of wheat flour from everywhere in the world, and we have done protein content and baking tests. And the reality is that there is no direct correlations between protein and the final product characteristics. And here, this is just, again, an illustration for the volume, for the slice area. Here, if we are between 10 and 11.5%, we can select two flours that are within this range, 10.1 and 11.1%, and we will end up with two completely different products. So no, we already know that, but this is proof enough that protein content is not enough. The result of that is that oftenly the specifications that we use, they are not really enough. I will come back to that, but the results of that is that there is an insatisfaction on the market of bakers in particular, and bakers are the one saying that's not me. This is actually the results of a survey that was done a couple of months, maybe a year ago, on LinkedIn, for which we had a lot of results, during which a simple question was asked. Does it happen that flour, despite meeting all laboratory specifications, still gives issues during baking? 96% of the answers were yes. And to some of them, it was very often for 25% of them. So that's not That's not nothing. And the problem of that is that if you have non-conform flour entering the production, then that means that you are going to increase the number of non-conform final products. And that has a cost that can be very high. Interestingly, when we looked for the profile of the 4% people who said, no, it never happens, we stumbled upon academics mostly. So not daily working with the process. So people actually putting in the books, you need a flour between 10 and 11.5. This is a good first approach, but this shows that reality needs something a little bit more robust. So the question becomes, okay, protein is not enough maybe, but why do our specifications fail? We have two main reasons, basically. First thing is that the information might be inadequate. This is what we were saying. Maybe protein content and quantity is not enough. We focus a lot on protein, but not really on the starch, which represents 70% of the flour. So if we don't analyze the starch part of the flour, that means that we assume that 70% of the flour is outside of our control. It can be a choice, but results show that it can be risky. And then another reason might be also because we do not have the right objectives. We have wrong goals. We don't have the right levels for the specification or the right uncertainties, the right tolerance around these results. And here, oftenly, the question that we need to ask ourselves is, who fixed the values? Who decided that specifications must be this, plus or minus this, and why? Is it the miller? Is it the baker? Is it based on real results, on what actually works on the line of production, or is it more theoretically? Is it a consultant? Is it someone else? But we need to reflect on how the specifications were built. Our proposal here is to do some reverse engineering, is to try and predict less. It's extremely complicated to predict based on the flour. If you have a flour, you can make all the analysis that you want. It's going to be extremely complicated to predict what the final product will look like. And the result of that is that we have 96% unhappy bakers. The solution we propose is at the same time easier and more logical, is to go from the end product to the flour, to understand what works well and what doesn't work based on the observation of the process. And this is a little bit what I would like to show you today. Is if we start with the end quality in mind, then that can be very, very straightforward. So the idea is to think, okay, it all starts with the end product. The end product must be perfect every time. It must be consistent in its attributes, and its attribute must have the desired level in terms of volume, of color, of this and that and that. Because what we want in the end is for this little boy to be happy, to like what he is hitting, and to ask mommy and daddy to buy the same product again next time. So this is what we want. To do that, to be able to always offer the same final product, it's possible if the baking process is under control. The baking process actually has a lot of variabilities inside. You have the machines, you have the human factor, you have the temperatures, you have the flour, of course, the raw materials, and so on. So a lot of things to control. If we get the baking process under control, that means that we have a flour quality that is adapted to this process. And to have a flour quality adapted to this process, then we need a milling process that is under control. And that also contains a lot of variable. And in the end, all of that is possible if we have the right width for making the right flour, for making the right final product. But again, that's not very complicated if we start by the end product. And this is a little bit what this series of webinar aims to describe. So the idea is to stop guessing and start knowing, to have objective data at every point of the process. We will not be able to discuss everything today, but that's a good thing, because if you were with us during the previous webinars, You know that we already discussed how to define and objectively measure what is a good final product thanks to vision inspection system. There is a recording available on YouTube for those who were not able to attend. Once we know our objective, then we can start analyzing the behavior of the dough during process, and we can design efficient specifications to select the flour. Both those objectives can be reached thanks to a radiological equipment called the MixoLab. And the recording of this presentation is also available on YouTube, so do not hesitate to go and watch it. But once we do have efficient specifications, we need to enter those specifications. We need to produce a flour that is compliant with the COAs, with the certificate of acceptance. And as a baker, we need to make sure that this flour corresponds to our certificate of acceptance. So this is a little bit the topic of today. And next webinar that should happen in January, we will discuss how to correctly select wheat to product compliant flour for a specific process. So this is the focus of today, how to produce compliant flours with the baker's COA. So here we can wonder how, based on what specifications, and so the question becomes, what are we measuring? What can we measure? And oops, I have a little issue with my animation, but basically this is what we are measuring. We can measure the dough behavior in the bakery line. We can do baking tests. This is the first thing. We can make baking tests. This may be complicated and a little bit long. It may sometimes lack a little bit of objectivity, but this remains one of the preferred solutions to validate a blend or to make sure that the flour is compliant with specifications. And then where we can help is with rheological tests, such as the one offered by the graph that you can see on the screen right here, or the MixoLab or the RioF4. So we have discussed quite intensively already of the MixoLab last time, so I invite you to see the corresponding recording, and about the RioF4 as well, as there is again a corresponding recording on this specific topic. So today we will be focusing on our graph, but just so you know, this is not the only rheological test that we have. And then we can also test the composition of a flour. So how much moisture, how much protein, how much damaged starch, then thanks to various technologies. And this is a little bit what we will describe right now. It's the different technologies, how do they work, and what are their limitations. So we will discuss measuring the composition of the flour thanks to an indirect measurement, which is provided by NIR measurements. Then we can measure the contents, actually measure it thanks to a reference method. And here we will be discussing damaged starch, and in the end we can see the combined effect of all those components thanks to rheological tools. And here we're going to focus on the Alver graph. So let's start with NIR. To understand NIR, this is not very complicated. We just need to know two basic principles. The first principle is that light is made up of a multitude of wavelengths. Have many different ones composing the spectrum of what we can see and what we cannot see, actually. And then the second thing we need to know is that every flour, every product in the world, they are composed of molecules, and the bonds between specific molecules, they vibrate, they absorb more or less light from certain wavelengths. They have a preferential for certain wavelengths. So that means that if we are able to connect a specific absorbance with a specific component, then we can measure the amount of components in the product. So how does that work exactly? Well, the first thing is that we need to produce a light. Every NIR tool, they need to produce light. And then we need to transform this light into a series of wavelengths. So we'll separate this light into many different wavelengths to create a spectrum. So with NIR instrument, usually we are between 700 and 2,500 nanometer. Yeah. Sorry. The second operation, once we have our wavelengths, is to send those wavelengths through the product or to the product, to scan the product with all the different wavelengths, and to measure the characteristic of the light after having gone through the product. What do we remain? If the absorbance has been really high on some wavelengths, then we are able to connect that with specific components such as moisture or fat or fiber. Once we have this absorbance, this curve, then what we need to do is just statistics. We need to analyze the largest possible number of samples with the infrared method and with the reference method, because we need to have a reference data. Here, this is an indirect measurement with an IR, always very quick, but indirect. So that means that we need a reference method in front of us. And with that data, with the reference data and the spectrum, the NIR spectrum obtained for all the samples, then we can create a calibration, what is called a calibration, that needs specific computer tools and capabilities called chemometrics to be designed. But in the end, for the users, that's just very simple. You analyze your sample and you have a result displayed. Very simple, very fast. Game changer for our business. A game changer, yes, but it has limitation. It has important limitation that we need to keep in mind. The first is that it relies on reference method data. So that means that NIR cannot be more precise than this reference method. We have had people in the past saying that they need very, very precise, very accurate measurement of ash content, for instance, like plus or minus 0.0000. I'm exaggerating, but you see the point. When the actual reference method, the one with the oven, actually has a wider acceptability. This is just not possible. We cannot achieve a higher resolution, a higher precision with a secondary method than with the reference method. That is just impossible. Then the second thing is to wonder, okay, we are depending on this reference method. Is this reference method precise? Because if we are trying to predict something that moves around, that has no fixed values, like some parameters such as stability with the pharenograph are incredibly variable, or the P/L of the alveo if you want. They have a high variability, they have a high accepted variability. So if you want to predict that thanks to a secondary method, then make sure that, well, that's going to be complicated. So make sure that what you want to predict gives already good results to begin with. And third but not least, the examples I have given, water absorption, P/L, those examples are actually not possible to predict. Because the thing is that because of how it works, because of the fact that we are going to measure the bonds between certain molecules, what we are measuring is not a quality. This is a quantity that we are measuring. So quantity of protein, yes. Quantity of water, yes. But quality of protein, no, absolutely not. Water absorption, no. Water absorption means that you have different things, such as damaged starch, such as protein, such as pentosanes, and so on, that are here impacting water absorption. So this is not something that can be predicted through NIR. It can be estimated at best. And there is a parameter that is just impossible to predict thanks to NIR, which is damaged starch. Because damaged starch and native starch, they have the same bonds. This is the same bonds between the molecules, and so they will react the same way. So this is just theoretically impossible to predict damaged starch from NIR. So for that, we need a different method. And here, the best method that we have is the method offered by the SDmatic, which is an amperometric method. So just here, as a reminder about damaged starch. So again, we always hear about proteins, but starch is incredibly functional. It has a big impact on the quality of the products, and it is the main component of the flour, around 70% of it. So controlling starch and controlling damaged starch is actually key in mastering flour behavior. And the thing is that whatever you do, however you temper your grain or blend your grain or mill your grain, you will always produce damaged starch during milling. You will produce more or less damaged starch depending on the hardness of the grain. If it's harder, then you will produce more damaged starch. It will also depend on the conditioning of the wheat and the adjustment of the milling process, but you will always produce damaged starch, meaning starch granules that have lost their integrity. It always happens during milling process. It cannot be avoided. And most of all is that once it has been created, once damaged starch has been created, we cannot correct it. There is nothing equivalent that could counteract all the impacts of damaged starch or increase all the impacts of damaged starch as well, as once. Not one magical powder. That's complicated and costly to correct once it's created. So the best way to control it, to have it under control, is to test it and prevent its apparition or control its apparition. Why it is so important to control is because damaged starch, again, is incredibly functional. It will impact the water absorption capacity a lot. If you have more damaged starch, then you have more water absorption. Damaged starch absorbs 3 to 4 times its weight in water, comparing to native starch. This is 10 times what native starch is able to do. So it does have a direct impact on the dough consistency and on the stickiness of the dough as well. Also, it will impact proofing. If you have more damaged starch, then that means that you have more availabilities, you have more surface open and accessible for enzymatic attack. And so damaged starch is more sensitive to amylase activity. That means that with the same amylase activity, with more damaged starch, you will produce more free sugars, which is the food of the yeast. And that will directly impact the dough stability, the volume, the texture of the final product. It will impact proofing in general, especially in formulations that do not contain a lot of sugar. And then it will also impact the final product characteristics. Because we have produced more free sugars, if this sugar is not consumed by the yeast, then it's available. And it's also available during baking. If you have more free sugars, that means more Maillard reaction, more caramelization, and that means that the color of the final product will be browner. So in the end, for any product, there is an optimum level of damaged starch. There is not too much or not enough. Damaged starch is not a bad thing. It's not a good thing. It's just like protein. It's something to have under control. And usually there is a specific balance between protein and damaged starch to achieve. If you have more protein, then that means that you are able to support more water absorption from the damaged starch, because this water then will be collected by the protein, which will prevent stickiness. So the general common rule is that if you have more proteins, then you can handle more damaged starch, and that will increase your overall water absorption, which is good. So for cookies, for instance, you don't have a lot of proteins, so you cannot handle a lot of damaged starch. For pan bread, on the contrary, you need a lot of proteins to have a developed structure, a developed texture of the product. And if you have more protein, that means that you can handle more damaged starch, which will increase your water absorption capacity and allow you to make more bread from less flour, or more bread from water if you want. To measure damaged starch, that's a little bit complicated. You don't have a lot of possibilities on the market. You have NIR, but again, NIR, I don't trust the results of NIR for damaged starch. We do not, as Chopin, trust the results of damage starch for NIR. And then you have enzymatic methods. Enzymatic methods are very powerful, but they are also long and costly and requires expert operators and a lot of complicated machines. So the best way here as a miller to detect damaged starch, very simple way and very fast, is through amperometric method. So this method that is used with the SDmatic is based on the principle described by Metcalfe and Giles in 1966, who proved that there was a correlation between iodine absorption and damaged starch content. The whole thing is based on the fact that starch has a certain affinity for iodine. And maybe you did this experiment in high school. I know I did a long time ago, but I did that to put a drop of iodine on top of a product containing starch. I think I did that with potato at the time. But you'll see the iodine, which is usually yellow, turn dark brown, dark purple, a little bit like the here in the image that you see. If you have more damaged starch, you have more affinity for iodine. You have more bonds that are created between damaged starch and iodine. And so this is what we do with the SDmatic. We measure, we produce iodine, we introduce the flour, and we see how much iodine we lose. If we lose a lot, then that means that we have a lot of damaged starch. If we don't lose a lot, that means that we don't have a lot of damaged starch. That's a little bit the idea. And that lasts about 15 minutes to perform. It's actually very straightforward to make the test. It's very simple. You just have to prepare a simple chemical solution, 1.5 grams citric acid, potassium iodide, distilled water, and 1 drop of thiosulfate. You place a reaction ball with the solution in the SDmatic 2. You configure your tests. You enter your flour weight. Just have to weight 1 gram of flour. So this is not a lot, let's say. So very nice for not a lot of product. Once it is done, you introduce the flour in the SDmatic 2 and you press play. And the rest of the test is automatic. It should last 15 minutes approximately. Time for the solution to be heated up to 35 degrees. At this point, iodine is being produced. So you can see here the solution turning yellow on the screen. Very nice yellow. Once the iodine has been produced, the flour is automatically introduced and you can see the solution turning, well, dark purple, black. And 3 minutes after the introduction, then we can see the result displayed on the screen. So yeah, very straightforward. And in the end, the results are displayed in absorption of iodine, but also UCD, UCDC, AACC values, Farhan values. So we have prediction of enzymatic method as well. And finally, so now we know how much of what is in the flour, but that doesn't tell us how those different components will behave and how they will interact. To know that, we need to go through rheological testing. So again, we have a lot of possibilities, Mixolab that we have discussed in other webinars, RioF4 as well that we have discussed in other webinars. But one of the main instruments used to do that in the market nowadays is the Alveol graph. So what is an Alveol graph? Very simply put, it's an instrument to measure the characteristics of the dough by blowing a bubble. So we will just measure the evolution of the internal pressure in the bubble as a function of the time. And we do that thanks to an instrument called the Alveol graph. So today we have 2 main models, the Alveol PC and the Alveol Lab. They do not have exactly the same possibilities. They do not exactly work the same way, but both are measuring the evolution of the internal pressure in the bubble as a function of the time. And in the end, we access a curve like that. A curve that increases at first, that allows us to characterize the tenacity, and for which the pressure will decrease during volume expansion. If we have more volume, you have less pressure inside of the bubble. all the way through the rupture. Here, this is the moment where the bubble bursts. And so, of course, you lose any pressure that you had in the bubble. And by doing that, we are measuring key parameters, again, such as the p-value, which stands for the tenacity. We will measure the extensibility, which is the maximum volume of air that the bubble can contain, and so on. So I will describe all of those parameters a little bit more in detail just after. But the standard test is also quite straightforward. It's known for a very long time, so I will not explain it in detail. But you just have to mix flour and salted water for 8 minutes and 24 degrees, extrude the patties, laminate them, shape them, cut them into small patties, let them rest for 20 minutes, and finally blow them, also in temperature and humidity controlled environments. So with the alveolar lab, it is done automatically. With an alveolar PT, you'll have to have a control of this environment surrounding the bubble. So this is a standardized protocol, of course, at many different levels, and that is used by many traders, millers, bakers all around the world. So this is a little bit here the description of what we get from this curve. First, we will get the consistency of the dough, if you will. So it's not exactly the consistency, it's the tenacity. Here, it's the necessary strength to start the expansion. You see, when you blow a balloon, it's exactly the same. At first, it's very hard because you need to break the superficial tension. With a bubble of dough, that's the same thing. We need to break the superficial tension, and that depends on the tenacity. The higher the tenacity and the higher pressure is necessary to break those tensions. This tenacity mainly depends on the water absorption capacity. If you have higher water absorption capacity, you will have a higher p-value. And that depends on the quantity and quality of proteins, on the damaged starch content, on the fibers, pentosanes and ash content, and so on. That's it's the tenacity. And then you have the extensibility, which corresponds to the length of the curve through the moment just before the rupture. The extensibility will mainly depend on the quantity and quality of proteins, and that represents really the ability, the potential of the dough to stretch to contain gas. Then we have a very interesting parameter, which is the elasticity index. The elasticity index is not used a lot, and that's a shame because that gives us a very nice complementary information. The elasticity, that's not the same thing as extensibility, that represents the ability of the dough to stretch above all, to return to its initial position after being deformed. And to measure the elasticity with the Alveolar graph, we actually measure the curvature of the curve, how the pressure decreases. So with a little bit more numbers, basically it is measured precisely 40 millimeter after the beginning of the curve. So we take 40 millimeter and we measure the pressure. At this moment, the amount of air injected into the bubble is always 200 milliliter because we work at constant airflow. We know that at 40 millimeter, we have injected 200 milliliter of air, always. Here you have two very similar curves, same p-value, same L value, and the only real difference is how the pressure goes down after reaching a maximum. It's basically how the dough is trying to resist to the deformation or not. So yeah, my computer is turning on again, so I have a lot of things happening right now, but yeah. All right, so here we have the orange curve that gives a certain bubble at 200 milliliter. We have a certain volume of air inside of the bubble, and we have a certain volume that is occupied by this bubble. So if we have less pressure, if we lose more rapidly the pressure, that means that the dough is trying to resist less to the deformation, is trying less to come back to its initial position. And so that means that at this moment, the bubble is bigger and resists less. So the pressure is lower. That's completely logical. And we have a lower elasticity index. Here, if we lose the pressure more rapidly, that means that the elasticity is less important. And so we have less elasticity. This is actually extremely important because you can have a good tenacity, you can have a good extensibility if after deformation, your dough elasticity is not controlled. You might end up with a lot of difficulties regarding the volume. It's actually very visible with a pizza. If with a pizza you have more or less elasticity, you will end up with a pizza of a more or less important diameter. If the diameter is too big, if you don't have enough elasticity, the pizza might not enter the box, which would be horrible. But on the contrary, if you produce a pizza that is too small, well, maybe it will enter the box, but a too small pizza is not something very good for customers. They don't like it. I would not like it. I had to have a very small pizza instead of the large one I ordered. Or I thought I was buying. And let's say it's really too small and you put pizza sauce on the pizza, but also around the pizza. Then you have to stop the line and to clean everything. So that's not good. Controlling elasticity for some applications should be mandatory. And then you have a parameter that is very well used, very well known of the alveograph values, which is a global value. This is the area under the curve, which is characterized by the W value. W comes from work or energy required to make the deformation, to blow the bubble until it's ruptured. And this is a very interesting parameter, very useful, but it should not be used alone because it's a very global value. You could have two curves, here the orange one and the blue one. They have the same W value, but one has a higher tenacity and a lower extensibility than the other. And so as a result, these flowers might have the same W value, but they will not end up with the same behavior. And maybe if I have another recommendation, it would be to analyze P value and L value separately rather than using the P by L, because P by L is also a global value for which you add the uncertainty of the P and of the L value. P alone or L alone are much more precise than the P by L. So my recommendation would be to focus on P, L, elasticity index, and then the W value. Forget about the P by L. So now that we have all of those information about the composition and about the behavior, basically I can measure it and so I can correct. And we have different ways of correcting. The first way is to not correct, is to actually choosing the right wheat, the right flour, and grinding it the right way. So here, maybe we need to know a little bit how those composition affects the rheology. So this is the trend that was observed in more than 150 samples of algal flowers versus the composition. So here we have algal values, P obtained were between 24 and 171, L between 25 and 227, etc., etc. It's just to say that we have gathered a high amount of samples, but that really represents the entire range of interest. And we have analyzed protein content, damaged starch, thanks to the SDmatic and ash contents. And what we see is that, one, it's extremely difficult to draw direct correlations between composition and rheology. But we have global trends. We know that, damaged starch and ash content, they will have a positive impact on the p-value. At the same time, we also see that damaged starch will have a negative impact on the extensibility. On the contrary, the protein content will have a positive impact on the extensibility, and it is actually quite well correlated with the W value. And that is why you can have an estimation of the W value, even if it's about quality with NIR. It's because it's very well related to protein content. But again, quantity and quality is not the same thing. So you can have an estimation with NIR, but definitely not the actual value. And you will only have W and not the other parameters. An estimation of the W. But once you know that, from a miller point of view, that means that you can also better control your milling procedure. What does that mean? That means that if you have a flour that contains more damaged starch, more high content, basically a flour with a higher extraction of the flour, you will end up with higher ash content, higher damaged starch, and that will increase your p-value and lower your L value. We know that we can play on adding vital gluten to the mix in order to increase p-value, in order to maybe increase or decrease, that depends on the gluten, on the vital gluten. We can also add enzymes and ingredients, but that can be costly and they are not all performing the same way. So the main idea would be here, you have the possibility to analyze all of your flour from different streams and to better control your blends. Once you have done that, once you have analyzed your flour, then you can do your blends. And how can you do that based on the alveograph results? So you have your specification, and here in the Alveolab software, you have a very nice tool that is called the blending tool that allows you to anticipate the result of a blend. So here, this is just an example. You have 3 flours, flour C, B, and A. That's not the right way, but that's okay. With their corresponding values for P, L, W, I, E, and so on. What you can do, this is the first thing, is that you can put the proportion that you want in your blend. You know that you want to blend 25% of flour C with 50% of flour B and 25% of flour A. And the software can calculate you directly what will be the end result. So you will obtain a flour with a p-value of 92 and an L value of 95 and so on. That's already very good and can allow you to save some time and not to analyze all your blends with the alveograph, maybe just the final one. But you can also use it in order to calculate the best blend. So here, let's say that we have 2 flours, flour A and B, and above all, you have a target. You have a target, you want to achieve a W value of 250. All right. How do we achieve 250 based on the results that we have here? You can click on look for the best blend in the software, and the software will directly recommend what is the percentage of product to use. Here, 31% of flour B and 69% of flour A, and the expected results. You will get a flour with a W value of 250 if you do this blend. But remember, we said that maybe the W value was not enough. So maybe we can do something a little bit more challenging with here 3 samples, but above all with 2 targets. Here we have 2 targets. We have a target on the W value and we have a target on the P value. And we want to achieve that thanks to those products. So here again, we can click on looking for the best blends, and the best match will appear on the screen, the best blend. And here you will get the blend expected results. So of course, the first time we were able to reach a W value of 250, but here this is not the only target. So we have made, the software has made a compromise to reach a p-value in the end of 95 and a W value of 283. And then finally, we can fine-tune, we can adjust the blends using improvers, enzymes, or chemicals in order to correct. And here the good news is that, so we are not specialists about enzymes and ingredients. We have done the work, and we have analyzed a lot of enzymes and ingredients, but more than that, experts, people doing the enzymes and ingredients have done so. And this is the case of Berlin Chemie, for instance. They have something called the Navigator, which is a very nice tool that you can find online, for which basically you can enter what you are looking for, rheology, the product that you want to see, and to choose your challenge and effect, what you want to do. And basically here, Mulenchemy is telling us that ascorbic acid will have a positive impact on the W, on the p-value, but a negative impact on the L-value. But calcium peroxide will decrease the W value, increase the p-value, and decrease the extensibility. Cysteine will decrease p-value and W value, but increase extensibility, and so on. So you can use that in order to target the best product to use. And we have actually done a little bit the same in the envelope software. You also have an additive guide. So this is a library of additives, a list of additives based on results that we have obtained in the past, and there are global effects on the p-value, the W value, and the L value. This is entirely customizable, meaning that you can delete everything and just enter your own product. And here you must be careful. If you analyze 2 vital gluten, you can see here vital wheat gluten with positive impact on P, positive impact on W, and positive impact on L. According to the couple flour plus enzyme or flour plus gluten, the effects might be different. So here I would recommend to check that with your specific improver and your specific flour before using it. Then once you have created your list, then you can use the guide in order to find the best ingredient. Basically you have 2 flours. You have here the blue one and the red one. The red is the objective, is what we want to achieve. And the blue is the flour that we have right now. So how do we go from here to here? And the software will automatically select different possibilities. Here, an amylase or a beta amylase could work and could have the relevant characteristics to allow you to decrease p-value and to increase L-value. So, as a conclusion, sorry for the technical difficulties, but what we wanted to share today is that before everything, we need a target, we need specifications, and this is the entire point. Trying and predict what will happen is extremely complicated, but setting up specifications based on what is working or not is not complicated. You just need to have a good collaboration between miller and baker. As a baker, you need to explain, this is the material that works for me. And as a miller, you need to understand that, yes, this is the flour that is required. And of course, and this is the impact of the flour and not something else. But once you have defined what is important for you, maybe it's damaged starch, maybe it's protein quality, maybe it's fiber content, maybe it's maybe it's the gelatinization of the starch or so on. Once you have defined what parameters are important for you, the most important thing is to ensure consistency. We want to always have the same flour. But with this system, we know where to focus on. We know that we need to focus on either damaged starch or this or that or that. And so there is no point in losing too much time in trying to control something that is not key. Maybe we sometimes spend too much time fine-tuning protein content, because protein content must be between 11.5 and 12. And so what happens at 12.01? Is the flour bad? No, I don't think so. Or not necessarily. But the idea here is to focus where we need to focus. Then the challenge, when we want to correct, is to establish relationships between different tools. You have the rheology that explains you how, that tells you this is how the dough is going to behave. It's going to have this tenacity, this extensibility, this behavior. And then you have composition that allow you to understand rheology. And so once you have defined the target, and once you have understood the mechanism, the link between composition and rheology, you can do many different things. You can select the right material, the right wheat, the right flour, right from the beginning. You can blend the different streams of the flour, or you can blend different wheats or different flours in order to get closer to what you need. You can work on the process, both on milling or baking, in order to adjust to specific flour. And you can even fine-tune with enzymes and additives. So this is not extremely complicated. This is way less complicated than trying to predict. It just requires a little bit of structure, good tools, and good support. And for those last 2 points, we are here to help and to assist. So do not hesitate to contact us if you have any need or if you'd like to improve your overall quality control strategy. So thank you very much for your attention. Again, sorry for the inconvenience, and I hope that it was clear. Thanks. So let me look at the questions now. I see that we have a couple of them. So first question, that is a very nice question, but not a question for me. How much costs SDmatic 2? I don't know. I'm not in sales. I'm not in sales, but if you can contact the address that is on the screen, sales@kpmanalytics.com, they will have a much more precise answer than I do. I don't want to say anything wrong, especially not online. Right now it is recorded and everything, so I'm not going to try. So I have other question is, how does damaged starch impact stickiness? Okay, so that's a very nice question as well. So the damaged starch impacts stickiness based on the fact that it can absorb a lot of water, but it's very hygroscopic. Damaged starch can really easily bind with water, but then during mixing, these bonds are being destroyed, and so the water is leaking out of the damaged starch. It's getting released by the damaged starch. And so that means that you need something else to absorb this water, this available water, protein in general. So if you have too much damaged starch and not enough protein to retrieve the water that was liberated by damaged starch, that means that you have too much free water. And this is what causes stickiness. This is the free water available in the dough. So this is why you require a proper balance between protein and damaged starch usually. I have another question. Why the elasticity index measured at 40 millimeter? Another good question. This is a balance. 40 millimeter is where we see usually a good curvature. We have started to have a good decrease of the pressure, but we don't want to analyze it too far, because if we go higher than 40, sometimes you have flowers with very low extensibility, and they can have an L value like just 40 or just after that. So if you take like 50 or 60, maybe you won't get a calculation of the IE value because it's too far away. So we needed to have a good decrease, but not going too far to not lose the information. So 40 is a good balance, usually. Another question is, Hello Lab, constant or adapted hydration? That's the question. Constant or adapted hydration? Okay, very good question. Actually, there is an entire webinar on this topic that is available on YouTube, so do not hesitate to check it. But the short answer is that there is not one protocol that is better than the other. That really depends on what you want to do. Originally, the Alver graph was designed to work at constant hydration, and it works very well at constant hydration. With some hard weights, we don't have a proper representativity of the elasticity of the extensibility in particular. So that depends. If you want to keep something simple and fast, then working at constant hydration is great. If you want to be in closer conditions of what bakers do, working at adapted hydration, this is what bakers do, then working at adapted hydration can be interesting. But that really depends on the specific goals here. Or if you are working with a specifically very strong hard weights, that can be interesting also to work at adapted hydration. The second part of the question is, some ingredients take time to reach give rheological effects, such as ascorbic acid. 20-minute rest is not so long. I agree, 20 minutes test is not long, and that's good. Usually we don't like to have very long tests. And I can assure you, and we have had a lot of proof, and you can look at the navigator of Melanchini if you'd like, that at 20 minutes we have all the information that we need to analyze most products. Then for some of them, if you need to work with longer resting phase, nothing prevents you to do so. You can absolutely, with any type of alveograph, have a longer resting phase, 60 minutes or 2 hours or whatever you like. There is actually a protocol to determine bugwit contamination with a 2 hours resting phase. Another question is, do we have similar information for gluten-free bread? That's a very interesting question. Yes and no. Yes, in the sense that, like every process, gluten-free processes, they will require a specific formulation, a specific composite flour to work properly. But you cannot necessarily use the same tools. Like the alveograph, for instance, was not made to work with gluten-free products. It is strictly impossible to blow a bubble of gluten-free flours. So when working with gluten-free product, I would rather recommend, and honestly really recommend, working with the MixerLab. You won't get much more information with the MixerLab. And plus, the MixerLab is able to heat and cool down the dough, which allow us to see the characteristics of the starch. Gluten-free products are mainly made of starch. So for me, MixerLab is the good tool to blend, to see the impact of enzymes and all of that, but with a different rheological system. Another question. How SDmatic affects hard bread in final products like paratha? How SDmatic affects hard bread in final products like paratha? So I'm not really familiar with paratha in particular. I'm not sure what are its characteristics. I'm actually doing a quick Google research at the same time, to be fully honest. Oh yeah, okay, that's particular. Well, I guess this is a sort of a flatbread. I guess that here what is important for paratha is, well, you need to control the consistency in any case. So well, that really depends on what you want to do, really. What is your problem? I cannot say this is the instrument for you or this is the way of working, because there is not one universal answer. But if you'd like to discuss a little bit more about your specific challenges, feel free to reach out or to precise in the Q&R, and I'll be happy to try and help. My answer would be whatever the final product. This is never a waste of time to control the flour, because whatever the final product and whatever the process, there is a specific flour that fits this process and this final product the best. So defining which specifications just requires to understand what are the challenges that you're facing. So don't hesitate to contact us for further information. Oh yeah, so that was for flatbread. So flatbread here, of course, volume is not so interesting, but diameter, just like pizza, is going to be key. So elasticity is going to be very important. The structure of the crumb, I see that this is a product with different layers. Structure of those layers will be important. So maybe here gelatinization will be interesting as well. But again, yes, I cannot say this is the best specification, but that can work as well. Okay, good question. If I were to get just one, which would it be between Alveo and MixerLab? I don't know. This all depends on your problem. If you're working on gluten-free, definitely mix it up. If your specific problem really depends on elasticity of the product, definitely overgrowth. So this is why we need to get a better, I will never tell you this is the solution. I will never say you don't have this, so you must have this. If you have today a quality control that allows you to have 100% satisfaction, then you are golden. And I don't have anything to teach you. But this discussion based on your specific challenges and based on your specific constraints, then we can design together what is the best solution. So again, do not hesitate to contact us. So I don't see any remaining questions at the moment, and we are at the end of our time, actually a little bit more than that. So of course, if you have any remaining questions, do not hesitate to contact us. Sales questions for sales at KPM Analytics. And if you have any technical questions, do not hesitate to contact me directly, and I will be happy to try and help. Thank you very much, everyone. And again, sorry for the inconvenience in the technicalities. Thank you so much. Goodbye.